Hi guys, welcome to my channel. Today we're going to be comparing the difficulty of a question from AMC 8, 10 and 12. These are maths competitions for high school students in America. Let's get straight into it. Suppose A, B and C are non-zero real numbers, and A plus B plus C is equal to 0. What are the possible values for A over mod A plus B over mod B plus C over mod C plus ABC over mod ABC? So we're given that A, B and C are all non-zero, and if they are to add up to 0, then either two of them are going to be positive and one's going to be negative, or two of them are going to be negative and one's going to be positive. So we can assume, without loss of generality, that for our first case, we have A is larger than 0, B is larger than 0, and C is less than 0. And for case 2, that A is less than 0, B is less than 0, and C is larger than 0. So let's start with case 1. From this, it also follows that ABC is less than 0. So this means that mod A is equal to A, mod B is equal to B, mod C is equal to negative C, and mod ABC is equal to negative ABC. So now our expression becomes A over A plus B over B plus C over minus C plus ABC over negative ABC. And this simplifies to 1 plus 1 minus 1 minus 1, or 0. And now for our second case. Well, in this case, ABC is going to be larger than 0. So we're going to have mod A is equal to negative A, mod B is equal to negative B, mod C is equal to C, and mod ABC is equal to ABC. So now our expression becomes A over minus A plus B over minus B plus C over C plus ABC over ABC. Now this simplifies to minus 1 minus 1 plus 1 plus 1, which is equal to 0. So our answer is A. So now looking at an AMC 10 question. The interior of a quadrilateral is bounded by the graphs of x plus ay squared is equal to 4a squared and ax minus y squared is equal to a squared, where a is a positive real number. What is the area of this region in terms of a? Valid for all a is larger than 0. So let's first consider the graph of the first equation. So we have x plus ay squared is equal to 4a squared. And square rooting both sides, we get that x plus ay is equal to plus or minus 2a. So the graph of this equation is going to be the two lines x plus ay equals 2a and x plus ay equals negative 2a. We can rearrange this to get y is equal to 2a minus x over a, or negative x over a plus 2. And likewise we can rearrange the other equation to get y is equal to negative 2a minus x over a, or negative x over a minus 2. And we'll label these as equations 1 and 2. Now, considering our second equation, we have ax minus y squared is equal to a squared. And again, rooting both sides, we get that ax minus y is equal to plus or minus a. So the graph of this equation is going to be the graph of the two lines ax minus y is equal to a and ax minus y is equal to minus a. So solving for y, we get that y is either equal to ax minus a or y is equal to ax plus a. And again, we'll label these equations 3 and 4. So given that a is larger than 0, we can have a go at graphing these. So let's graph 1 and 2 to start with. So since a is positive, their gradient is going to be negative, and starting with 1, its y-intercept is going to be 2. So it's going to look something like this. And the graph of 2 will be parallel, but with a y-intercept at minus 2. And from the gradients, we can see that the graphs of 3 and 4 are going to be perpendicular to the graphs of 1 and 2. Graph of 4 has y-intercept a, and assuming that a is larger than 2, our graph of 4 is going to look something like this. And our graph of 3 is again going to be parallel to the graph of 4, but with a y-intercept at minus a. And note that the lines are perpendicular, so these angles are 90 degrees. And this is the area we are trying to find. So we can clearly see that the shape is a rectangle. So if we can find its height and width, we can find its area. So first, let's label all the vertices as A, B, C, and D. Now, if we find vertices A, B, and C, we can then find the distance between them to find the height and width, multiply these, and get the area. So, to find vertex A, we need to find where the lines 1 and 4 intersect. So to do this, we need to set minus x over A plus 2 is equal to ax plus a. Multiplying by an a gives us minus x plus 2a is equal to a squared x plus a squared. Isolating the x gives us a squared x plus x is equal to 2a minus a squared, and x is equal to 2a minus a squared over a squared plus 1. Now substituting back into equation 1, we get that y is equal to a minus 2 over a squared plus 1 plus 2, or 2a squared plus a over a squared plus 1. The point A is 2a minus a squared over a squared plus 1, 2a squared plus a over a squared plus 1. So now let's find point B. To do this, we need to find where the lines 2 and 4 intersect. So when this happens, we're going to have minus x over a minus 2 is equal to ax plus a. Again, we multiply by a to get minus x minus 2a is equal to a squared x plus a squared. Isolating the x gives us a squared x plus x is equal to minus 2a minus a squared. And so x is equal to minus 2a minus a squared over a squared plus 1. Substituting into equation 2, we get y is equal to a plus 2 over a squared plus 1 minus 2, which is equal to minus 2a squared plus a over a squared plus 1. So therefore, point B is minus 2a minus a squared over a squared plus 1 minus 2a squared plus a over a squared plus 1. Now let's find point C, which is where lines 3 and 2 intersect. So when this happens, we're going to have ax minus a is equal to minus x over a minus 2. Again, multiplying by a, we get a squared x minus a squared is equal to minus x minus 2a. Isolating our x's, we get a squared x plus x is equal to a squared minus 2a. And this gives us that x is equal to a squared minus 2a over a squared plus 1. Subbing back into equation 2, we get y is equal to 2 minus a over a squared plus 1 minus 2, or minus 2a squared minus a over a squared plus 1. So we have that C is a squared minus 2a over a squared plus 1 minus 2a squared minus a over a squared plus 1. So now we can find the lengths AB and BC. So we'll start with AB. Length AB is going to be given by the square root of 2a minus a squared over a squared plus 1 minus 2a minus a squared over a squared plus 1, all squared, plus 2a squared plus a over a squared plus 1 minus 2a squared plus a over a squared plus 1, all squared. This is equal to the square root of 4a over a squared plus 1 squared plus 4a squared over a squared plus 1 squared. This can be written as the square root of 16a squared plus 16a to the 4 over a squared plus 1. And this is equal to 4a multiplied by the square root of 1 plus a squared over a squared plus 1. And now let's try to find BC. So the length of BC is going to be given by the square root of a squared minus 2a over a squared plus 1 minus 2a minus a squared over a squared plus 1, all squared, plus negative 2a squared minus a over a squared plus 1 minus 2a squared plus a over a squared plus 1, all squared. This is going to give us the square root of 2a squared over a squared plus 1, all squared, plus minus 2a over a squared plus 1 squared. This is equivalent to the square root of 4a to the 4 plus 4a squared over a squared plus 1. And this is equal to 2a multiplied by the square root of a squared plus 1 over a squared plus 1. So now BC times AB, which recall is the area we're seeking, is going to be 2a times the square root of a squared plus 1 over a squared plus 1 times 4a times the square root of 1 plus a squared over a squared plus 1. This gives us 8a squared multiplied by a squared plus 1 over a squared plus 1 squared. We can cancel out a squared plus 1 from the top and from the bottom. So this gives us our final answer of 8a squared over a squared plus 1, which is option D. And now, finally, we're going to be looking at a question from AMC 12. If circular arcs AC and BC have centers at B and A respectively, then there exists a circle tangent to both the arcs AC and BC and to the line segment AB. If the length of the arc BC is 12, then what is the circumference of the circle? So if we draw in the lines AC and BC, we note that triangle ABC is equilateral, and this is because all three of the lines are radii of the same circle. So this means each of its angles are 60 degrees. We're also given that the length of arc BC is 12. So by symmetry, the length of arc AC is also 12. Now, let R1 be the length of the radius of the larger circle, which is going to be AB, and also AC and BC. And from this, we can find the length of R1. We know that the length of arc BC is 12, and we know that it's also equal to 2 pi R1 multiplied by 60 over 360. Rearranging gives us that R1 is equal to 36 over pi. And now let's draw in the center of the smaller circle and call it M, and call its radius R2. So if we extend AM such that it hits BC, we know that this red distance is going to be 36 over pi. And then if we subtract this green distance, which we know is R2, this gives us that AM is 36 over pi minus R2. And if we call this point X, we know that AX is equal to R1 over 2, which is going to be 18 over pi. And since AB is tangent to the circle, this means that angle MXA is a right angle. So using Pythagoras' theorem, we have that 18 over pi squared plus R2 squared is equal to 36 over pi minus R2 squared. Expanding both sides, we get 324 over pi squared plus R2 squared is equal to 1296 over pi squared minus 72 R2 over pi plus R2 squared. Now we can cancel out the R2 squareds from both sides. Rearranging, we get that 72 R2 over pi is equal to 972 over pi squared, or R2 is equal to 27 over 2 pi. But note that we're being asked for the circumference of the circle. We know the formula for the circumference is going to be 2 pi r. So substituting in gives us 2 pi times 27 over 2 pi. Obviously, the 2 pi's cancel to give us 27. So our final answer is D. So how did you find these questions? Let me know in the comments below. If you enjoyed, please like and subscribe and share it to a friend to see if they can solve them too.